Thanks, everybody. Yeah.
All right, everybody. Okay. Couple things about the quiz. I know that the quiz auto grader marked you down for capitalization. Don't worry, I'm going back through and fixing that. Same for and that's just the way that Canvas's auto grader works. If you're supposed to type in a specific thing, I would have to guess every possible way you could get the right answer typed wrong in order for you to not get automatically, like just putting spaces in between stuff throws it off, right? So I'm aware of that. Don't panic. I'm going back through. I just also started the end of the alphabet going for this way because the end of the alphabet always gets their stuff graded last. So all that's getting fixed, and then your atoms quizzes, as predicted, I did not get them done over the weekend, but I'll try to have them done for you on Wednesday. And then also be caught up on your other quizzes by then as well. So let's talk about some random questions first. And some of them are not as random as others because Schrodinger's cat's actually relevant. We talked a lot about quantum stuff the last couple of weeks, right? Schrodinger's cat was a thought experiment, and it gets misunderstood a little bit. Erwin Schrodinger was one of the founding fathers of quantum mechanics, along with Bohr and Einstein and all those folks. And basically, Schrodinger actually was trying to illustrate that quantum mechanics doesn't make sense in the everyday world. He was actually trying to use this as an example of how dumb it would be to actually apply quantum mechanics ideas to the everyday world. Because basically what it is, he said, okay, you've got a box that you can't see through. You put a cat in the box. You also put the sort of a poison gas that's going to be released after a random amount of time in the box with the cat. So, and then you close the box, you seal it. You don't know after, say, 30 seconds has passed. You don't know if the gas has been released or not, right? So is the cat alive or dead? He's dead or is it alive? If there's say it's a 50-50 shot after 30 seconds. If the cat's alive versus dead. Is the cat alive or dead? I could alive or dead, right? It's one of the two. So what quantum mechanics says, the way that we treat electrons as probabilities, it's basically it's the equivalent of saying the cat is alive and the cat is dead simultaneously. If you have a 50-50 shot, then it's not one or the other, it's both at the same amount, at the same time, which doesn't really make any sense with the macroscopic world. That's not how the macroscopic world operates, right?
So yeah. Like, the same. If I flip a coin and then before it lands, it can be both at the same time.
Correct. So it's based, yeah. So like if you flip a coin, is it heads or tails while it's in the air? It's both. It has both possibilities. And even quantum mechanics would say, even after it lands, if I slap my hand down on it before anybody can see it, it's both. Until you actually measure if it is heads or tails, it's simultaneously heads and tails. Asa?
What is the likelihood of the cat being dead steadily increase though over time?
There's a problem taking that all the way out, taking the analogy too far. The point is that we would never say that the cat is both alive and dead at the same time, right? We can say that with things that have yet to happen, like the coin being flipped, but it's weird to think about what after the coin lands, but before I check it, it's both. But mathematically, that's true. Mathematically, it doesn't matter whether the coin's done spinning or if it's hit the table and I've covered it up. In both cases, there's a 50-50 chance that it's heads, right? And so that's really what quantum mechanics is saying, is that we can treat these probabilities like they're true, at least mathematically. And that is also where Einstein had a big problem with quantum mechanics because he didn't like the idea of probability clouds and two things being simultaneously true.
Probabilities, is there a way to find the end result, like to make it very literal, example in the box, and how does that work?
Yes, so that's it. So if the two probability functions, if your electron could either be here or there, until you check it's in both places at the same time. And both of those functions that they use to describe that are called wave functions. By actually checking where it is, they call that collapsing the wave function, because now all of a sudden there's not two probabilities, there's only one possibility because it's been measured.
So, can't we, if we go off mathematically, right, like if we have enough, I know this isn't like foolproof, but if we do it enough times to be able to recognize like a pattern of the result, and we make an assumption on where the electron could be or whether or not the cat is alive or dead based on how many times we open the box and see the cat's alive.
But that's like saying the next pitch is going to be a strike before it's thrown.
Right, so that's like
We can guess
can
with a
make
certain level of certainty.
uncertain. Right?
Right.
Is that a practice or is that just?
Yeah, and actually that's what the shape of those orbitals is actually your best guess for where they're, and it's really not saying that, you know, those p orbitals that are figure 8 shaped like this, they call that a volume. It's not an area, 3 dimensions. This volume is our best guess for where the electron is, but there's a chance that the electron is outside that. If we wanted to increase the chance that we've said, and usually it's like 95% chance that the electron is within the shape. If we wanted it to be a 98% chance, we would just have to make these bigger. And now there's a 98% chance that the electrons are in there, but it's still not 100. Unless you make your box the size of the entire universe, there's not a 100% chance that you're going to find the electron in that space.
What if you measure both like poles at the same time? Like, if you measure-
Meaning like both, so measuring both like the momentum and its position at the same time.
Yeah.
So turns out you can't do that. It doesn't work if you try to do that. There's always one of them that's going to be measured before the other by some instantaneous amount, and the act of measuring one of them throws off the other. It turns, and it's not just that observing the system changes, it's also that there's that inherent uncertainty built into everything in the universe. That everything in the universe has uncertainty as to both its momentum and its position, and you can't know both at the same time. With things that are larger and heavier, you can know with a lot more certainty both of them at the same time, where you still have the same degree of uncertainty, but it's a smaller percentage of the total property. With something as small as an electron, though, the uncertainty itself is a significant fraction of that actual property. Does that make sense? 2 questions about nuclear chemistry. We'll talk more in detail about carbon dating when we get to nuclear chemistry. But basically, carbon dating works because there's a certain fraction of carbon atoms in the upper atmosphere that get generated. They're a radioactive isotope, carbon-14, and they gets generated by the radiation from the sun. The radiation from the sun, when it hits the upper atmosphere, turns a certain chunk of nitrogen atoms into carbon-14. Carbon-14 then breaks down and eventually turns back into being nitrogen, but it's got a half-life of about 5,700 years, meaning that after about 6,000 years, half of that carbon-14 has turned back into nitrogen. Where it becomes useful is that plants, when they photosynthesize, take carbon from the atmosphere in the form of CO2 and turn it into sugars. And everything that's living on Earth either photosynthesizes or eats sugars that are produced by photosynthesizing plants. So every living thing on Earth constantly is intaking a certain ratio of carbon-14 just by eating and living and breathing. When you stop eating and living and breathing, you stop taking carbon-14 in. Which means if we know how much carbon-14 we started with, so at time equals 0, we have a certain amount of carbon-14, original or initial. And over time, that gradually declines. And after about 5,000 years, or 6,000 years, I think it's 5,730, you're at half of what you started with. So basically, by knowing how much carbon-14 something started with and knowing how much carbon-14 it currently has, we can estimate how long has passed since that object stopped breathing and photosynthesizing. Similar idea, except that you have to go with stuff that has even longer half-lives. So carbon-14 dating only works till you get to about 10 half-lives. Until you get, if it's something older than 50,000 years old, you can't use carbon dating. You use uranium lead dating or you use potassium dating. There's several others that actually started decaying at the formation of the solar system in some cases. That allow us, and we can say, okay, well, if this rock has this ratio of lead to uranium, this rock was formed this many years ago. But it's a similar idea. If you know what the starting amount was and you know what the half-life is, we can actually predict how long it's been since an event started that process. Nuclear energy is a really good question. 20 years ago would have been a really good time to invest a whole bunch in nuclear power plants for nations around the world. As it is now, if we built more nuclear power plants, that takes so long for nuclear power plants to pay off. They generate a ton of electricity, but they're also really, really expensive. And the way that renewables are making ground and more research and more renewables are being adopted all the time, it's unlikely that we're going to see a whole lot more in the way of traditional nuclear power plants, just because renewables are becoming cheaper and faster and are progressing faster as well.
Like small private.
An argument has been made. I don't think any of those are going to keep pace with wind farms and solar farms as far as cheapest way to make electricity. With the caveat that if fusion ever gets reliably and sustainably made, if we're able to make fusion power plants, then electricity is pennies on the dollar to what it is now. It's essentially would be a free energy for everybody because electricity would be so cheap. So that would be a game changer, and that would be worth investing in. As it is now, it seems unlikely that a whole lot more nuclear power plants are going to be. I still think it's going to be an important tool because wind and solar are by nature somewhat unpredictable. And so I think in the future, the electricity grid is going to have multiple sources forever. There's going to be geothermal mixed in with all these others. And I think nuclear has a role there, but I don't know how long it's going to be before that actually gets built. Vinny and then Quinn.
What's the difference between a nuclear plant and fusion plant?
So traditional nuclear power plants are fission reactions, which means they're uranium and other large atoms splitting into smaller atoms, like we talked about last week. That produces a ton of energy according to E equals MC squared. But fusion would be taking small pieces and smashing them together to make big pieces, which is effectively what the sun is. And that gets even another 100 times more effective. And the byproducts that we get from fusion reactions are relatively harmless, as opposed to making all this nuclear waste that we then have to store and figure out what to do with. So fusion has a couple of advantages over traditional nuclear plants. Quinn? Oh, sorry. I thought I saw your hand up. Zachary. Yeah, so tritium is a type of hydrogen. But there's a lot of research. Fusion, the running joke in engineering and science circles was that since the 1950s, fusion reactors have been 20 years away. No matter when you ask somebody in the last 70 years, it's always 20 years away. Only in the last 10 years or so did they start saying fusion reactors are 5 years away. So if we continue that extrapolation, maybe within my lifetime we might see nuclear or fusion reactors. But they are making tangible progress. I also saw that there was a research group in France, I think, that was able to keep a sustained fusion reaction going for 20 minutes. And ideally, if we can just continue some of that to keep it going indefinitely is the idea. And then we could actually get a ton of energy. But yeah, there was something in Berkeley or at Livermore Labs about the actual numbers. I think that was, but that was at a very small scale. That was not actually at the industrial scale. Yeah. All really fascinating stuff. And energy is going to be a really big deal. Obviously, it already is a really big deal. But this is going to be really interesting. I see a question over here. Yeah. Because you don't have to refuel it. Basically, you only have to refuel nuclear fuel rods every 10 years or so. So in theory, those nuclear subs and nuclear aircraft carriers can stay out until they run out of food, basically, and not have to come in to refuel at any point. Plus, it generates. So if you look at the scale of a nuclear aircraft carrier, it's the size of a small city. It's got 20,000 people stationed on it at any given time, and so they basically need to carry their own power plant with them. And if they were using diesel generators, they'd be stopping every 2 weeks to top up their diesel supplies. Somebody asked about light bulbs. Who really invented light bulbs? Basically, the idea of a traditional old incandescent light bulb is basically run current through something that has resistance until it glows, until it gets hot enough to glow. That idea predates Thomas Edison by a fair bit. Thomas Edison was one, and this is one of the few things. Thomas Edison gets a bad rap for stealing other people's inventions, and he did a ton of that. As soon as he got enough capital, he started buying up other people's patents like crazy. So a lot of stuff that gets attributed to Thomas Edison actually wasn't Thomas Edison, but the first commercially viable light bulb and the whole lighting system was actually put forward by Edison. What Edison was smart enough to do, not only did he make the light bulb, he presented it as a finished package. He said, here's how you put power into the entire house and how you electrify an entire house to light the entire house. And so if you bought his light bulbs, you were also buying his power distribution system, which then gave him enough clout that he was able to kind of stay on top of things moving forward. But he probably did actually do most of the work there. And there were a couple of key inventions there. Gloria? They really did not like each other. And that's not really blown out of proportion. They really didn't like each other, but they were mostly arguing not about light bulbs, but about AC versus DC. Because, and really that what we've eventually settled on as a society and actually worldwide is a mixture of AC versus DC. AC is a lot safer. AC stands for alternating current, and that's what you have in wall sockets for the most part. AC is not great for charging batteries, and it's not great for transmitting energy over large distances. We use DC for both of those. On any of your chargers, this thing is effectively a transformer. It takes the alternating current from the wall and turns it into DC that can charge the battery on your computer. And we also use DC. All the power lines that bring power into houses or into neighborhoods or schools are DC that then hits a transformer and turns it into AC. So really we wound up with both versions, and that actually makes the most sense. But yeah, Thomas Edison famously electrocuted an elephant. I think he brought in an elephant and he applied an AC current till it died as a way to demonstrate that AC was inherently unsafe, or maybe I have those backwards, but basically he vilified Nikola Tesla to the point, and Thomas Edison is a nice British American name. Nikola Tesla was scary and European. So between that and the fact that Thomas Edison's had a head start in terms of he already had a ton of money, he was able to basically bury Nikola Tesla and some of his ideas. And I guess one of the things I will say about light bulbs burning slow is they don't actually burn. That's actually one of the tricks, is that inside of traditional incandescent light bulb, they actually were either filled with a vacuum or they were filled with an inert gas like a noble gas to prevent the light bulb filaments from burning. Because otherwise, if you heated that filament up, it oxidized almost immediately and burnt out almost immediately. So that's actually one of Edison's big contributions, is he figured out a way to use a specific type of pump to commercially produce light bulbs that had a good vacuum in them, therefore they lasted longer. And then he paired it with, plus you can only use these great light bulbs I just invented if you also buy my lighting system. A little bit, Apple takes a lot of cues from Thomas Edison that way. We're going to take this really cool idea and we're going to make it just proprietary enough that you have to keep everything within the Apple ecosystem. Thomas Edison was a pioneer in economics, probably more than he was in science. All right. We'll go fast on these next ones. New materials like biodegradable plastics or batteries, that's entirely chemistry. But it's applied chemistry. So sometimes you see that in chemical engineering fields, sometimes in material science fields. But if you're interested in producing new materials, that's all chemistry. And it's all, how do we make this material? How do we make this material cheaply? How do we make it so this material will last long enough, but not too long in the case of biodegradable stuff? How do we do it sustainably or using stuff that's cheap to find in the case of batteries? We don't want to have to use really, really expensive elements in the case of batteries. So if new materials, and it's going to be a field that continues to blow up for a long time, is its own field of study called material science, and it's really, really cool. How is matter held together? It depends on what scale you're talking about. On a really small scale, the scale of a nucleus, it's a strong and weak nuclear force. At the scale of atoms interacting with other atoms, it's all electrons and charge and electromagnetic force. If you want to talk about how a planet's held together, it's that fourth force, gravity. So basically, it depends on what scale you're talking about. But the four fundamental forces are what hold to get everything together. The reason that we have matter and planets and molecules and nuclei in general is because of the balance of those four forces. And sometimes some really interesting stuff happens when those four forces interact with each other. Like a neutron star is what happens when strong nuclear force and gravity wind up interacting together. You get a neutron star. Which is, and it's kind of cool. A neutron star is basically an atomic nucleus with no protons. It's the mass of our moon or larger. But it's one nucleus. Everything held together by strong force, but there's no protons pushing away. So it doesn't fall apart the way that our larger isotopes do. Last but not least. So is there a limit? This kind of ties into that as well. Is there a limit to how many elements you can compound together? Not really. The largest compound in terms of biochemistry is going to be a protein. And usually there are several thousand, up to 100,000 atoms in one molecule. That is what makes up most proteins in your body. But then you could also make the argument that the entire crust of the earth is one large molecule of silicon dioxide with a little bit of impurities here and there. So there's not really an upper end once you start scaling stuff up. All right, we ended with this slide the other day. Practice with this ionic nomenclature. It seemed like the quiz went pretty well for everybody. Everybody I've seen so far, other than a couple of small things here and there. If you write something like zinc 2 oxide, that's like a quarter of a point off because it's a little bit redundant because zinc is always +2, but it's better to be redundant than to be ambiguous, right? So when in doubt, make sure you include the numbers in the parentheses. Which brings me to the next question. What's the rule for using Roman numerals? Because Roman numerals are dumb. They are dumb. Sorry, I misspoke. Paraphrased. If you don't know the rules for Roman numerals, it's okay to just write the regular Arabic numerals in parentheses. Instead of saying iron 3, if you forget to write it out, you can just say iron 3 in parentheses with Arabic numerals. Right? But if you want to use Roman numerals, I don't even want to go into talking about Roman numerals. Roman numerals are dumb. I'll stand by that. However, was there a question? Because they don't have the concept of 0 in there. That's why we use Arabic numerals, because Arabic numerals use the concept of 0 as a placeholder so that you can just scale up. You don't need a separate character for 50 in Arabic numerals because you can just do that. In Roman numerals, you needed a separate character because for 10, and a separate character for 100, and a separate character for 1,000, and so on. So, what's 5 in Roman numerals? B. If you put a 1 before the V, it means 1 less than that. If you put a 1 after the V, it means 1 more than that. Gloria? They shouldn't. That's incorrect.
I've seen that on my old.
Really? That's because the old clock that I grew up with in my parents' house was the reason I had to learn Roman numerals, because that was the only clock in the house. And it had, not the only clock in the house, but for a long time, that was the one that was visible for most of the house. Yeah, you should not put 4 numbers, 4 in a row. You can have IV as 4, BI is 6, BII is 7, BIII is 8. Like I said, it's a silly system. Now that we understand what a 0 is, the best that the Romans could do with what they had, minus the concept of a 0 as a placeholder. So I don't want to be too harsh on them, but there's no reason to still be using that when we have better options. So you don't want to use Roman numerals, especially for anything past 3. Anything up to 3, just I. Leonard?
Make it a more clear distinction by subscripts and things like that.
Probably, but if you're writing out the name of the element, it's already distinct from the subscripts. So I don't know why you can't just do that. I will accept either of those. I'm still going to write it inside in Roman numerals because that's the way I was taught, and that is still technically the standard. But when you're writing down names, either of these is fine. It's full credit answer. Anybody know how you would write? So I guess it gets really weird when you get up to like 500, because the Super Bowl is the only thing that actually consistently uses Roman numerals above like 5, really, at this point. Above 12 for sure. L is 50. X is 10. I think. So C for 100, like century. I think that 500 is a D. And then M is 1,000. I don't know what 5,000 is. But you see how it doesn't repeat? You need a new letter every time you go up a factor of 10. It doesn't make any sense.
They didn't do like 5 with the additive of whatever 1,000 was, so they would be like 80.
No, that's what they were missing. That's what I mean by the concept of 0. It's not that they didn't understand nothing. They didn't understand how you could use a 0 to make something, increase by a factor of 10. They didn't understand 0 as a placeholder. And that's one of those, you don't think of the concept of 0 as being a technology advancement, but it absolutely was. And it's one of those that was discovered not simultaneously, but independently in several different times throughout history. I think the Mayans had a concept of 0. The Chinese and Arabic or Persian all discovered it separately. Yeah. Anybody want to take a stab at that one? We don't know for sure, but I have a pretty good idea. Why would we use 10 for our base? 10 fingers. If we'd had 12 fingers total, we probably would be using a base 12 system and so on. And now those work the same. Has anybody taken any math classes that use different bases? Or binary is just base 2? You still use digits. You just get to, when you get to 10, it's not 10. You are using base 8. You would write your first letter or your numbers at 1, 2, 3, 4, 5, 6, 7, 10. 9 would be written as 1, 1. What's that? Base sets of 4? Oh, base 64. You use placeholder characters instead of, because we don't have numbers to go all the way up there. So if you use like base 16 is an easier one. It goes 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 A, B, C, D, E, F, G. That's 7? Yeah. And then you get to 10. Or sorry, you don't do the G's. F and then 10. You write it as 10, but really 10 was A. It gets a little tricky to use language because our language is not set up for it either. Anyway. All right. Should we do some more math or should we talk about polyatomic? Polyatomics? All right, we'll save the math for on Wednesday. How many of you know about moles? Okay. That's the only math we have to do is just talking about moles. So we'll talk about that on Wednesday in more detail. Let's talk more about nomenclature, which gets us to another quiz question. Somebody asked about how does understanding the periodic table help us predict the typos of chemical bonds that will form between different elements. Anybody have any guesses? How does knowing the periodic table help us know what types of bonds are going to form? Charges. How do the charges affect things? How do we know if it's an ionic bond? What do you need to have an ionic bond? You've got to have something that wants to be a positive charge and something that wants to be a negative charge. So at the most basic, the periodic table helps us know if it's going to be an ionic compound, because if it's ionic, you've got to have something from the left-hand side of the stair-step line, and you've got to have something from the right-hand side of the stair-step. You need a metal and a non-metal. Is one of the easier ways to think about it. As we talk about polyatomic ions, it gets a little bit more complicated, but that's your go-to. If it's an ionic compound, it's going to be a metal and a non-metal. And all you do is you say the names of those two things. If it's not a metal and a non-metal, if it's two metals, what happens? Sorry, if it's two non-metals, we get the covalent bond. When they merge together. Exactly. And so really what's happening when we do that is that by moving these nuclei closer together, we allow those electrons to be in both valences at the same time, right? And so what that looks like is a graph. Basically, we can think about the energy of this system, and things that are most stable have the lowest energy. So if you want to actually make things as stable as possible, the easiest way to think about this is just two hydrogen atoms. Each hydrogen atom is trying to gain an electron to have a full valence, right? As you move those two hydrogen atoms closer and closer together, that actually becomes lower and lower in energy until you get to the point where you're at this minimum, this lowest possible energy, where you've got the electrons sort of surrounding both nuclei at the same time. Well, they're kind of in between both nuclei at the same time, but that allows them to be in both valences. It allows you to double count, basically. The hydrogen atom on the left has two electrons in its valence, and the hydrogen on the right also has 2 electrons in its valence. Even though there's only 2 electrons total, they're sharing them. Right? And that creates this minimum where it's more stable, where it's lower energy by bringing these 2 nuclei closer together. What happens when you start getting them 2 nuclei too close together, though? Why does it start going back up in energy when you go the other direction? Or when you keep going? That would mean that the nuclei or the electrons are actually better distributed around the 2 nuclei, wouldn't it? And isn't that a good thing? So what else is happening when we get those 2 nuclei closer together? What's the charge on the nuclei? +1 on each of them, right? What do positives do to other positives? They push each other apart, right? So as we get closer and closer together, it gets lower and lower energy because we get these electrons that can be in the same orbital, in the same place. But as we get the nuclei too close together, the nuclei start pushing each other away. So there's sort of this balancing act. And that's why there's sort of a position where everything sort of cancels out, where the 2 nuclei are still pushing each other away, but there's an attractive force from getting those electrons close enough they can be in both valences at the same time. And that creates this sort of equilibrium distance, this average distance between the 2 nuclei, where you're balancing those forces out. All right, and that's what a covalent bond is. A covalent bond just occurs when you can get these different electrons that are each in their own individual orbitals, and we basically add those orbitals together. You bring an s orbital that looks like a sphere up to another s orbital that looks like a sphere, and when you get them close enough, they kind of merge together. You average them out to make this sort of cloud shape where your electrons are between, or they're kind of surrounding both nuclei at the same time. Looks like that should be a face or something. No? I'm not an artist. All right. So how does going back to this question here, how does knowing the periodic table tell us when covalent bonds are going to be formed? When you have 2 nonmetals. And that's all that polyatomic ions really are, is collection of atoms and molecules in general. We call them molecular compounds or covalent compounds, is when you have a bunch of nonmetals that all arrange their electrons in such a way that everything can be satisfied at once. Right? And that's the example of where we have a lot of different possibilities, right? Where we can say, okay, well, we can have N2O, or we can have NO2, or we can have N2O4, or N2O3. And even sometimes, and so that's why we use the prefixes for these, right? We talked about this a little bit on Friday, using those Greek prefixes. There we go. I got this little out of order. These Greek prefixes. Right, we just specify. You have a covalent compound. You know it's a covalent compound because it's got all nonmetals. And we just say how many of everything we have. So dinitrogen monoxide, or nitrogen dioxide. So because there's more than one possible combination, we need to specify how many of everything we have. There you go.
If the amount of, nitrogen to oxygen amounts are ratios, then how is, N2O4 different than N2O2?
Good question. So in that case, what we'd say is that the empirical formula is the same for these two. It's the same overall ratio. The difference is with these covalent compounds, they're actually present as distinct objects, separate from each other. So when you have solid N2O4, it's still a bunch of N2O4 molecules all arranged together. As opposed to ionic compounds, if you have solid NaCl, you actually have like a whole lattice structure, this grid, where you're alternating a sodium and a chloride and a chloride and a sodium and a chloride. And these repeat in 3 dimensions almost infinitely because of how small atoms are. So for ionic compounds, we always want to take the lowest whole number ratio. We would never say Na2Cl2. But for covalent compounds, because they exist as distinct objects from each other, we actually, NO2 is actually different than N2O4. In theory, yeah. Another good example is that we'll talk about how to draw these structures in a minute. But C2H2 is a common molecule called acetylene. And the structure for it looks like this. But C6H6 is also a really common molecule. C6H6 is called benzene. And so benzene looks like very different. Thank you. This is one of the first molecules you learn in OChem. When you take OChem, benzene, there's a ton of OChem based around benzene. They behave very, very differently. Even though they've got the same ratio of carbons to hydrogens, if you have solid benzene, it's a bunch of these floating around. Or it's liquid benzene. If you have liquid acetylene, it's a bunch of these floating.
So is it dependent on how they bond together?
Exactly. Exactly. And OChem even has its own specific rules that are even a little bit more specific when it comes to naming. Because you can actually have something with the exact same formula that's 2 different molecules. You can have this molecule is called ethanol, which is the scientific name for drinking alcohol. The overall formula for this is C2H6O. You can also take same atoms and rearrange them to put the oxygen in the middle of the 2 carbons. And now it's dimethyl ether, which is a totally different compound that has the same exact formula, C2H6O. So how they're connected winds up being really important. So for now, we're gonna learn basic covalent nomenclature, which just is going to be based around these. I'm not going to ask you to learn organic nomenclature. My OChem students have been in my class for 6 months and they're still learning organic nomenclature. That's a whole different thing. Yeah, miss. I've been doing it long enough that they're just kind of rattling around. But yes, you do kind of have to memorize, or at least how to get the right names. It turns out there's a systematic way of naming a lot of these. And if you know those rules, you don't actually have to memorize the structures. Although it does wind up helping sometimes. So all this to say, this is why we don't reduce that ratio for covalent compounds. We reduce the ratio for ionic compounds to just to our lowest whole number ratio. All right, and that also gets us into polyatomic ions. As promised. So we'll do a week from Thursday. So you have 2 weeks. I know. It's partly for safety reasons because I need you to know the difference between phosphate and phosphite if you're going to do labs. Because there will be some times when where phosphate and phosphite will both be on the lab cart, and if you mix them up, you get a very, very different reaction and not necessarily a safe reaction. So, and it's not something, you're not always going to have this list with you like you will a periodic table. Every science classroom you've ever walked into had a periodic table on the wall, right? Not all of them have lists of polyatomic ions on the wall. And this is not an exhaustive list. This is a small subset of polyatomic ions. There's a ton of them. A polyatomic ion is just any covalent compound that has an overall charge. That's all these are. These are still just covalent compounds. But because they have an overall charge to them, we can't just say, like for sulfate, SO4 2-, we can't just say sulfur tetraoxide, because the fact that it has a charge makes it different, right? And so this slide is on the PDF, and you get some printed copies for you tomorrow to study on. Make those flashcards. There are some similarities that allow, or some patterns that allow you to limit some of the memorizing. Yeah. These are the only ones that'll be on the quiz. Every single one. All what I'm going to do to make the quiz for this one is I'm just going to go through, and I'm either going to erase the name or erase the formula, and then I'm going to randomize them. So if I give you the formula, you write the name. If I give you the name, you write the formula, including the charge. Knowing the charge winds up being important. Right? Especially if we're going to say something like sodium nitrate. We say sodium nitrate, and we're trying to figure out what that formula is. What's the first step if you're trying to go from the name to the formula of an ionic compound? You write both ions out and you see what ratio you have to have them in, right? That you will have a periodic table. It will actually a little bit, because what you'll notice, well, you might not notice until somebody points it out to you. It turns out odd numbers of electrons are really unstable, because you can't have everything with a full valence if you have an odd number of electrons, right? Because electrons naturally work best in pairs. So all of these, the total number of electrons is an even number. So how does that help you? Well, if you're trying to figure out what the charge is on nitrate, we can look at it and say, okay, well, oxygens are always an even number, right? How many electrons does nitrogen have? 7, 5 that are in the valence, right? Which is an odd number. If nitrogen has an odd number of electrons, nitrate has to have an overall odd charge. Because as it sits, there's 18 valence electrons. There's another 5 electrons. If nitrate had an even charge, if we had 2 more electrons on there, we'd still have an odd number of electrons overall, right? So if nitrogen has an odd number of electrons, the overall charge has to be an odd number. Now, it doesn't necessarily help you whether it's at -1 or -3, but at least takes -2 out of the picture. How useful is that going to be compared to just memorizing it? Your mileage may vary, but it is a good connection. And when push comes to shove, if you're not sure, like almost all of these have charges, almost all of them are negative for starters. And they pretty much all have charges between -1 and -3. Right, so if you know that, then at the very least, your sulfate example, anything with sulfur, how many valence electrons does sulfur have? 6, so an even number. So what's the charge have to be on anything that's all sulfur and oxygen? Got to be even. And we don't have any -4s up there, so it's got to be -2. Are you going to have time to do all that logic on the quiz? No, but a few times you might. If you have most of them memorized and you're blanking on the charge for sulfate, here's your way you can logic it out with just a periodic table. Some of the other connections that help is that if you know what the formula is for the 8, the version that ends in "ite" is everything's the same except you're missing an oxygen. So sulfite is sulfate missing an oxygen. Okay, so if you memorize everything that ends in 8 and you know that rule, that actually helps a lot. I don't need to memorize the formula for phosphate as long as I know phosphite. Sorry, other way around. I don't need to memorize the formula for phosphite as long as I know it's phosphate. And the 8s tend to be the most common and most stable of that series. So sulfate is more common than sulfite in general. Does anybody know anything that has sulfites in them naturally? They tend to get used as preservatives. So you actually see some sulfites are left in bottled wines. They use sulfites to actually stop the fermentation process a little bit. It kind of prevents the microbes from continuing the process and makes it last longer. You see the same thing in deli meats. Deli meats have nitrites and sulfites in them usually. Pickling salt. Because they tend to be more reactive and they keep things from growing. Which is good when you're talking about food, usually. All right. What else is there on here? Talk about. Oh, there's a few of them. Polyatomic ions that have a -2 or a -3 charge. They usually have a version as well where you just add an H+ to it. You add a hydrogen ion to it. So sulfate becomes HSO4. Now it's -1 because we added a +1 charge to it. We added a hydrogen ion. And we just name it hydrogen sulfate.
Oh, yeah.
Hydrogen carbonate, hydrogen phosphate, and dihydrogen phosphate, because phosphate has a -3 charge, so you can actually do that twice. And so that right there, if you know the rules between 8 and 8, and you know this hydrogen rule, that just cut down your memorizing by like half right there. What else is there on there? The more extreme case of the 8 and 8 rule, there's actually a way to modify it further that you see with the chlorates in the top right of that chart. So chlorate is ClO3 -1 charge, which means chlorite, ClO2 with a -1 charge. If you have an extra oxygen, we just add per to the front of it. It's actually from the same root as hyper. So you can think of it, hyper means extra, right? So perchlorate gets 1 extra oxygen. And then if you take 1 extra oxygen away, we get ClO -1. That's hypochlorite. Hypo means missing, right? Like hypoglycemic. So what's the common name for hypoglycemic? Anybody know? Happens, yeah. Low blood sugar. Hangry, basically. Hypochlorite means is chlorite missing an extra oxygen. Right? So if you memorize chlorate and you know how these roots work, you actually have all four of them memorized. Right? And there are some, like the bromates are not on here. There's bromates and iodates that work the same way. Hypoiodate is just IO with a -1 charge. But they're not on your list to memorize. All right, so how does this work? Why do we care? How do we use this to name things? How do we name ionic compounds in general? If I said CaCl2, how do you name that? Say the name of the first ion, then you say the name of the second ion, right? Naming ionic compounds with polyatomic ions works the exact same way, follows the exact same rule. You just say the name of both ions. We just have another list of ions that we can throw in there now, right? So you can have the active ingredient in bleach, for instance, is sodium hypochlorite. What would the formula be for sodium hypochlorite? Well, there's hypochlorite, and sodium's a +1, right? So -1 and a +1, we need a 1-to-1 ratio, right? So it would just be NaClO. So it's adding more vocabulary to the way we name ionic compounds, but it's not really changing the overall process. You say the name of the two ions. Say the positive ion, then the negative ion. Fun fact. You can actually have Google refuse to answer a question for you. If you ask Google if it can tell you the formula for sodium hypobromite, what would hypobromite be? What would the formula be? So what's the formula for sodium hypobromite? Nah, bro. You will remember that though. You laugh, you groan. You will remember that. Nah. So here's some more practice. We'll do a couple of these now, and then we're going to go talk about Lewis-Sott structures. So SO4 2-. If you have that memorized, you know that that's sulfate. If you don't, you soon will. So what's the ratio? 1-to-1. So Mg SO4. Magnesium. Let's do manganese 4 sulfate. Manganese 4 sulfate. It's still sulfate, so it's still SO4 with the 2-. And then Mn4+. So we need a 2-to-1 ratio. Mn parentheses, SO4, 2. So the same way that we don't reduce the numbers when we're talking about covalent compounds, why C2H2 gets left as C2H2, it's the same reason why we don't distribute that too. We don't want to write MnS2O8 because S2O8 could be its own thing. Right, so we keep it like this so we can see, oh, that's SO4. I know that that's sulfate and I know what the charge is. Right, so keep those, don't distribute. Use this print. It looks clunky to write it that way, but that is the proper way of writing it. Side note, anybody know what magnesium sulfate is? It's at Rayleigh's in its relatively pure form. Not table salt. It does go by the name. Say it again. Close. That's actually bismuth in it. As a bismate, as a polyatomic ion, actually. It's Epsom salts. Epsom salts are magnesium sulfate. So why are they called salt when it doesn't have any sodium in there? Because and really it's just ionic compounds in general. When you have an ionic compound in its solid form, the old school way that would be to classify that as a salt. So sodium chloride is the most important salt to us for taste reasons and just because we need sodium as a nutrient. But technically any ionic compound is a salt by that old term. So Epsom salts. Don't put Epsom salts on your food. They won't kill you, but sulfate is a very strong laxative and it tastes awful. You can use, they use Epsom salts in brewing beer. You need to make your water have the right mineral profile to brew certain types of beer. And you can actually just go grab Epsom salts from the grocery store to do that. Fun fact, magnesium sulfate is one of the reasons why Dublin brews the best stouts in the world. Doesn't matter as much to you at this point because nobody in here has ever tasted beer, I'm sure. But you can't brew a light beer using the water from the river in Dublin because it's got too much magnesium sulfate in it. So you're stuck brewing dark beers if you're in certain cities, or you have to use distilled water. Which, considering just been making Guinness in Dublin for 400 years, that was kind of a big reach back then. So, fun fact about history of civilization. Does anybody know why the first cities were formed? Why we as a species went from being hunter-gatherers to being closer to rivers? That helped. So the old idea was actually that it was because we learned how to farm. Because rather than hunting and gathering and then risking starving to death because you can't find food, it's really convenient to be able to grow food consistently and know how much food you're going to be able to produce. Except there's now new research suggesting that all of those cities started not just because they discovered agriculture, but because they discovered brewing. So it wasn't just food, it was actually more, because when you think about it, what's more fun, farming grain or walking through a forest and eating berries and things, right? The berries tasted better. The reason they actually settled down was actually beer. That's my anthropology talk for the day. All right. Let me go back to talking about Lewis dot structures. So how many of you did Lewis dot structures before? No? Okay. I'm asking a lot of this computer. All right. So if we want to predict how these different molecules are bound together, what their shapes are, it turns out that actually has important effects on things like boiling point, on things like will it dissolve in water. Something about this slide really messes with it. We can represent the electrons around each atom by using these dots, right? And so this process is called a Lewis structure. And it's just a way to graphically show how the electrons are distributed. And at its most basic, you start by just saying, okay, well, if I have two fluorines, each fluorine has a total of 7 valence electrons, which means each fluorine, I'm using X's to represent the electrons on this other fluorine. Both of these fluorines want to gain a single electron. And the easiest way that they can both be satisfied is by sharing those electrons. So we represent a bond. I'm missing an electron here. We represent a bond with I'll call it a line or a stick. We call this the stick model sometimes. This bond represents a pair of electrons that are in both valences at the same time. And they're drawn as a bond, not just by doing it like this, because they don't actually keep the same shape. They actually sort of distort the orbital shape when you start making these bonds. They get elongated a little bit. So drawing a pair of electrons as a line actually makes sense from the quantum mechanics point of view to some extent. And really, it's more like a circle that has 2 electrons in it, one spin up and one spin down. But that's not really a good shorthand. Right, so when it's something as simple as 2 fluorines sharing electrons, it's easy enough to draw it like this. I don't really like using Lewis structures for individual atoms. So we could draw a Lewis structure for, say, magnesium. Where's magnesium on the periodic table? Second column, right? Number 12. So we could draw a Lewis structure for magnesium. It doesn't really tell us anything, though, just that it has 2 valence electrons. When we start getting into covalent compounds and we're starting to count how many electrons need to be shared, that's when these Lewis structures wind up coming in handy. Before we jump into that, though, looking at the periodic table, what's going to be able to make bonds with itself like this? Like fluorine bonded to another fluorine. Everything in row 17. Technically, all nonmetals. All nonmetals are trying to gain electrons, right? And so if you put a bunch of those atoms with each other, they're going to share the electrons that they have. So the most common ones are column 17, called the halogens. So fluorine, when you have pure fluorine, it's naturally present as F2, not as just fluorine. Same for chlorine, bromine, iodine. In theory, astatine, but astatine is really unstable. We don't really see astatine that much. Other other nonmetals will do the same thing. What other nonmetals do you know of that actually exist in this kind of
O2.
O2, O2, H2, N2. These are the most common ones. These are the ones that exist as gases, well, other than bromine and iodine. They're really commonly found in what's called their diatomic state. Basically, if you say fluorine, it means F2. It doesn't mean just an F by itself. If we're talking about these elements in their neutral atomic state, their elemental state, fluorine means Cl2. If we mean just a single fluorine atom, we'll actually say atomic fluorine. We'll actually be more specific. But is there any reason why something like carbon? I heard somebody say C2. Is there a reason why carbon can't exist in a diatomic state? It winds up making 4 bonds instead of 3 or 2 or 1 like the rest of these. But even stuff like sulfur and phosphorus basically those other non-metals, they make bonds in such a way that you actually make this like crystal structure instead. So you don't actually get C2, you actually get diamond or graphite. Okay. So if it was, so this is not atomic fluorine. Atomic fluorine would just look like this. Normal fluorine, if I just say fluorine gas or pure fluorine, that actually means this. Because it naturally, if you put a bunch of these together, they're naturally going to form this. Right? And the same is true for sulfurs and phosphorus and carbon. And the rest of the nonmetals, they just wind up making solid forms instead of making distinct molecules like this, so we don't specify as much. And sulfur has 3 forms of solid that are present. Phosphorus has 3 forms. There's white phosphorus, red phosphorus, and violet phosphorus. No, black phosphorus. So fluorine doesn't really do that, but ozone or oxygen does. You can actually have ozone looks like this. Where these are just the other electron pairs. I draw them in this little shape so that you can see them a little bit better. That's O3, and it's neutral as well. That's actually ozone. So O2 is the more stable state, but it does have other forms. We just have more specific names for them, if that's the case.
Well, how do you get something triple bond that, like, I know nitrogen has a triple bond.
So let's talk about these. Well, we're almost out of time to talk about Lewis dot structures. So we'll talk about those in more depth on Wednesday as well. But basically, if you bring 2 nitrogens close to each other, nitrogen's got 5 valence electrons. So if you just turn one of those into a bond, you still have another set of unpaired electrons. So you basically force it to share again. And that gets you a double bond, but then we still have an unpaired electron. So we force it to share again to get a triple bond.
Well, it's not always,
It is.
unless it has 2.
It takes 2 of them to make a triple bond. Oxygen has 2 vacancies in its valence shell. So oxygen will naturally form a double bond with another oxygen. So O2 looks like this.
What do you think due consideration? Attention students, if you are a track runner or a baseball student and are taking a bus to the middle school, please get on the bus K. Again, you're gonna get on bus K to go to the middle school for track and baseball. Thank you.
Do you have any baseball students? I had like 3 baseball players last year, but none this year. All right, that's a good enough place to end for today. We'll go in depth more about these Lewis structures and molds on Wednesday. Yes. Mhm. So either of those mean the same thing, right? So I don't, either way, I want to make them 6 things, right? Yeah. But yeah, that's either one of those works.
I see it, right?
This doesn't seem like the biggest number. You just round it up 5 to 8 or 0.0058. But I think you missed the conversion somewhere. It's right there. You didn't cube 1.6. And then I bet you didn't cube that number. Remember, if you're going to do the line conversion as the volume, is that cube the full thing. It's 1,000 cube. Make sense?
Thanks.
Don't be lazy. Like say.